All right. All right, everybody. It looks like we're live, so we'll get started here. As people are joining in, um, let me just give you guys a lay of the land here. In the chat session here, you can post your questions either in the Q&A tab or directly in the chat, and I'll be monitoring that during the talk. So feel free to ask questions as we go through the material that I've prepped here. Um, I think I probably have enough content, but we can always modify what we have and the examples that we have depending on the questions that you guys have as well, right? So feel free to ask questions, throw out questions as I'm going through the material. Don't feel like you have to wait till the end or we have to stick to exactly what I've got here. Right? Okay, awesome. So I think I've got something really exciting for you guys. Um, I wanted to start off with a general poll. How many how many of the attendees here know what a vector database is? So if you can type yes, no in the chat, that'll give me a understanding of no, no, a little. Okay, yeah. Okay, so Dan knows about it. No. Okay, cool. So that's perfect because I'm going to be basically we have two sessions here. The first session, the first 30, 40 minutes, we're going to talk about what a vector database is. Before I started working on vector databases, I didn't know what a vector database is. It's a new technology, but you'd be surprised how easy it is to pick up and how intuitive it is. So I'm going to spend the first 40 minutes here going over what vector databases are, and then I'm going to talk about how you can use a vector database to implement a recommender system. So how many people here know what a recommender system is? Yes and no's in the chat like before. Yes, yes. A lot more yeses. Yeah. So that's what I was expecting. So that's good. Okay. So I don't have a lot of I'm not going to provide you a lot of background on recommender systems. We're going to when we get to that part of the talk, we're going to jump right in and we're going to talk about how you implement a recommender system using a vector database. So I think everything is in order. So we're good to go. So let's kick things off here. A little bit about myself. I'm calling in from Toronto, Canada. I am a engineer and data scientist by training, and currently I'm working as a senior developer advocate at Weaviate. Weaviate is a vector database provider. Um, a lot of my training and a lot of my past experience has been in the field of data science and machine learning, particularly applied to healthcare applications. So I've worked on video data sets and imaging data sets in order to diagnose patients. A lot of the work that I've done in the past has been looking at dementia and seeing if you can take ubiquitous sensors like wearables, like smartwatches or cameras, to assess if patients are getting better or worse over time. Another field of my work has been on using uh, digital medical devices, so things like digital stethoscopes, digital blood pressure monitors, glucometers, to feed into a central network that could be used to monitor patients and see if a telemedicine intervention or a patient needs to be called into the clinic. Um, yeah, and I'm really happy to be here with you guys at KGC. I love speaking. I love learning, and I'm really happy that I got to share this with you guys. Okay, so like I mentioned, the first 20 30 minutes here are going to be items 1 and 2. So I'm going to talk about what vector databases are. I'm not going to assume that you have any prior knowledge about this, and then I'll show you how easy it is to get started with a vector database. So we're going to actually take a natural language data set, put it into a vector database, and we're going to perform search over that. And then after that, in the second part of the session, I'm going to talk about recommender systems and how we can implement them using vector databases. And then I'm going to show you a recommender system that I implemented, um, and I'll show you the code behind it and how the application actually works. Okay, so let's jump in. I'm going to motivate this concept of vector databases a little bit. Um, so a lot of you are probably familiar with the concept of keyword search. Let's say I give you thousands and thousands of documents. If you're performing keyword search, you're essentially looking for a specific word that occurs across your documents, and you're extracting documents that have that word, and you're returning that to the user. Semantic search is just a smarter version of keyword search. And so we're going to talk about how vector databases enable semantic search. So let me give you an example. So let's say you have lots and lots of documents like this. Each document has a title, and it's got the body of the document. Right? So we're going to start off. We have uh, articles or articles about the REST API. We have articles about programming languages for data scientists, so on and so forth. Imagine you have 100,000, a million, 10 million of these documents. Now, if we're doing keyword search on this, let's say you've put all of this into a traditional database. So imagine you've got a SQL database, a structured database. You've put all of these documents in there, and you're looking for the word Python in there. So here, it's essentially going to look over every document, and it's going to try to find wherever it can see the word Python. The problem with keyword search is that if the actual word doesn't exist, it's going to come up with nothing. It's going to return nothing. And the reason for this is because it actually doesn't understand what you're asking for. All it's doing is a very basic string matching. It doesn't understand that you're asking for the Python programming language, and so it should return something like this. In order to get that type of functionality, we have to move over to semantic search. And the idea behind semantic search is that your database or whatever you're interfacing with, wherever you type this into, actually understands the content of your document. It would be like giving all of the documents to a person and then asking them, give me the document that is most relevant to Python. They'll be able to read the documents and say, okay, you probably don't mean the animal, you probably mean the programming language. Here is the most relevant article for the programming language. And so semantic search actually understands what you mean in the query, and it searches through the meaning of the documents and it matches that way. So it's a much more organic and natural way to search over your documents. And here I mentioned that it's machine learning based. We're going to get to that soon enough. Um, the takeaway from this slide is just instead of doing a basic string matching, we're doing semantic matching of meanings. And so this is what vector databases enable, right? The ability to do semantic search over your data. The problem with creating a solution that is able to understand your data is, first of all, if you take any form of unstructured data, whether it be written text, like I just showed you, images, audio data, it's very hard to, first of all, process that data. Storing lots and lots of images is very different from storing lots and lots of structured data in the form of a CSV file, right? So first of all, processing that data is quite difficult. The second thing here is probably the most difficult thing, right? To understand that data is even more difficult. How do you differentiate the contents of two images? How do you tell the difference between two articles and whether one has more to do with the Python programming language and the other one does not? So searching through data, understanding data is very difficult. And then the third task that we have here is that even after we've understood that data, we need to be able to search over it efficiently. And the last part here is super important because if you're going to be searching through documents at a database scale, at a production level scale, you're not just searching through 1,000 documents or 10,000 documents. You're potentially searching through a million, 10 million, 100 million documents. So, however you solve that first problem of processing, understanding, and searching data, it only matters if you can do it in a scalable manner. Right? It has to be able to scale up to hundreds of millions of documents. And I'll show you a solution that does exactly this. So instead of just dealing with a vector library, you need to start talking about a vector database. So I'm going to break this problem down into two parts. The first part of understanding, processing, and searching through data, we solve that using machine learning. And machine learning gives us a way to understand what we mean by a piece of data. So if I give it a written text, it'll understand the context behind that text. If I give it an image, it'll be able to understand what's in that image. And these machine learning models are trained to understand the context. They actually so the way they do that is, let's say let's say we take a very simple example. Let's say you take a machine learning model and it's been trained to distinguish between a cat and a dog. It can identify which pixels and which patterns of pixels are found in cat images versus dog images. And so the next time you give it an image, it'll be able to tell you whether it's closer to that of a dog or a cat. So it actually understands the context as opposed to just doing a simple matching like we talked about in keyword search. So the idea here is that you can take any of your unstructured data. This can be documents, natural language documents. This can be CSV files. This can be images. And in this example that I've shown here, you're going to give all of this unstructured data to your machine learning model. And the machine learning model is going to turn every single data into a vectorized component. It's going to turn it into a vector. And so every object here, let's say you have the word chicken in your data, that is going to be turned into a vector representation for the word chicken, and you can plot that out on your vector space, also known as an embedding space. So every single document that exists here is human understandable. We're going to give it to the machine learning model. It is going to turn it into a vector version of itself, which is machine understandable. And we're going to take each one of these guys and just kind of plot them out. Here, I'm just showing a 3D vector space, but in reality, these vector spaces are 700 dimensional, 1000 dimensional. They're very large vector spaces. So imagine each one of these data points is 300 data points as opposed to just a 3D object in space. The point of doing this is that in vector space, your machine learning model understands that if you gave it an image of a chicken, that the vector for that is going to be close in proximity to the actual chicken word. Right? If you give it the word for cat and the image of a cat, those two vectors that are projected into your vector space are going to be closer together. It knows that a cat, the word cat is different from the word apple, so those two vectors are going to be farther away. It knows that the word apple and the image of an apple are closer together, so it's going to situate these closer in space. The cool thing about the example that I'm showing here is that it can deal with both images and text. So it understands that the word chicken and the image of a chicken are similar. Not a lot of models can do that. They're known as multimodal models. They can take in both image data and text data. Um, in one of the examples, in one of the demos that I'll show you, I'm actually going to be using a multimodal machine learning model to vectorize images and text. So the main takeaway here is that we're using machine learning to translate our data into vectors, and the reason why the machine learning model the reason why we want to do this is because the ML model can understand the context behind the data, and it positions our data in vector space so that it actually leverages context. Right? So data points that should be closer together, concepts that are similar are going to be closer together, concepts that are further apart are going to be separated in vector space. And so this is the bare bones of what a vector database is. In a vector database, you have your data. It can be images, natural language, but you also have a vectorized representation of that data. So the way I like to think about vector databases is that they store a human understandable form of your data as well as a machine understandable form of your data, right, which are the vectors. And anytime you conduct a search over your documents or over your data, it's going to use the machine understandable version of your documents to search over. Okay. So I see that there's a question that popped up. Okay, so this is from before. If there are any questions, just feel free to post them in the chat or in the Q&A section. Okay, so now that we have these vector representations for all of our data, what we're going to do here is we essentially need a way to scale this, right? Because you see probably 100 documents in front of you. In a real vector database, we're going to store millions and millions of objects. And not only that, but we need to be able to search over them with millions of queries per second. And this is the main difference. This is the main difference between a vector library versus a vector database. A vector database needs to be able to scale up to a big data scale where you have millions and hundreds of millions of objects and search over them. So there's a question: Is the SOLR, index a vector database. I'm not sure what you're referring to there. I'll talk about vector indexes in a second. That's how we scale up. Okay. Yeah. Yeah. So Mark's saying that no, it's just text indexing. Yeah. Thanks, Mark. Okay, awesome. So the three questions we need to answer here are: how do we store lots and lots of both normal data and vectorized data? We need to be able to do this on a scale where our machine learning models can take in millions of data points, turn them into vectors, store them into our database, and then conduct search over them. And then because this is a real database, we need to be able to support the insertion, deletion, updates of all of these millions of data objects. So the first answer of what vector databases are is that you have your original human understandable data along with the vector data that's stored in them. And the second challenge of how do you scale this up so that it's not just a sklearn solution that's implemented in a Jupyter notebook. In order to take it into a production level scale, you have to implement what's called a vector database. So in a vector database, you have not just the data objects, your unstructured data objects, but also their vector embeddings. So you'll have an image along with the vector representation for that image. You'll have a sentence along with the vector representation for that sentence. And the reason why you need these vector embeddings is because th- they are what you search over. Right? So we talked about this concept of vector search. Essentially, a vector database takes vector search and it scales it up so that you can perform it over hundreds of millions of objects. And so the two things that we need to add to this concept here is that we need real-time CRUD support. We need to be able to add thousands of objects, remove, update objects as we would in a SQL-like database, and then we need a way to scale our search uh, because we'll talk about in a second where if you know about the k nearest neighbors algorithm, that is very compute intensive and it takes a lot of time. There's no way that we'll be able to scale up a k-nearest neighbors search over millions and millions of documents. So we're gonna forego on recall and accuracy a little bit so that we can actually implement something that's usable in production, and that's known as approximate nearest neighbors. Okay, so that's a more complete picture of what a vector database is. You've got your human understandable data, you've got your machine understandable data that both lives in your vector database. We're going to search over this by first of all filtering our data, and then looking over the vectors, and then we're going to support CRUD operations as well as approximate nearest neighbor search. Right? So let me go through this one by one, and let's talk about how searching over your vector database actually looks. Right? So let's say you take your data, you vectorize it through a machine learning model, and you can do that through any of the open source models or any of the closed source models. At this point, there's APIs that are available where you can pass in your data. You'll get your vector embedding and you pop that into a vector database. So you take all of your data, you vectorize it, you now have a vector space. Now you're going to take a query, which is a question that you're searching over your data with. So think of this as a SQL query, but instead it's all it needs to be is, so that red dot there is our query, and it need not be structured like a SQL query. You can simply query your vector database with the word kitten, and that's good enough. Right? And so it's going to take the word, the query actually, and it's going to vectorize it using the exact same machine learning model, and it's going to pop it into that embedding space. And the idea here is that if you're asking a question about cats or the images of cats, the vector representation for that query is going to live close to the potential answers that come from your data. And so once you vectorize your query, all you need to do here is to look at which data points in your vector database are in close proximity. And these are potentially good objects or good answers to what this query is asking for. If I'm searching for the word kitten, then based on the data that I've already put into my vector database, I can get the word cat, the image of a cat, I'll get the word dog, so on and so forth. It depends on how far you're looking for and how many answers you're looking for, right? So if I only want the top two results, I'll get the closest two vectors, and then as I look farther and farther away, I'll get more irrelevant data points. So really, when we're searching over a vector database, we're not examining every single object that we have in our vector database, because that would take way too long. You would put in a query and then hours and hours later, you would still be waiting for a response. So the way to scale this is, instead of doing a k nearest neighbor search, we're going to do an approximate nearest neighbor search. And an approximate nearest neighbor search is just an algorithm that takes your data point, and instead of searching over every single possible neighbor, so all of these data points that we've shown here, it takes a hierarchical approach, a multi-layered approach, where the first thing it's going to compare to is a very low number of data points, and then it's going to drill down and add more and more data points. So eventually you'll get closest to the data point where your query is, but it's not guaranteed. K nearest neighbors gives you a guarantee of giving you the closest K neighbors, but in approximate nearest neighbors, as the name implies, you get the approximate neighbors. So that the price you pay for time and running more efficient queries is a loss in recall and a loss in accuracy. There's a question in the chat. How do you determine the dimension of the vector space? So the dimension of the vector space is determined by the machine learning model. When you're training a neural network or any machine learning model, you can specify what the shape of the input is and what the shape of the output is. If you're using an off-the-shelf model from Hugging Face or from OpenAI or from Cohere, they're going to tell you what the shape of the vector space is, because it's their models that they've trained. If you're training your own models, you decide what the dimensionality of your vector space is. If you have a very low dimensional vector space, it's not going to be able to represent a lot of information. If you have a high dimensional vector space, it'll be able to represent lots and lots of complex patterns in your data. Another question from Brian. What would happen if a database had never seen the word kitten? So that's the nice part here, right? You don't need to see the word kitten. So as it exists, the word kitten does not exist in the database. The idea here is that the machine learning model understands the concept of a kitten, a cat, and because it's been trained on a very, very large data set, it has a general knowledge. And when you pass in the word kitten, it vectorizes kitten into a corresponding vector, and that vector is going to be close to concepts that are related to kitten. And that's the whole magic of a vector database. You can query it in human language. You can talk to a vector database, as opposed to with a SQL database, you would have to structure your query and then do pattern matching. Right? So kitten still needs to be in the large language models training set. Yeah. So the token for the word kitten, the machine learning model needs to understand it. The vector database need not, right? We're piggybacking off of the power of the machine learning model and its ability to comprehend the word. Another question here. But would one ever use multiple vectors for the same object, two different points in the same vector space? So the important point here is that this embedding space is generated from one machine learning model. Right? And in this particular case, it's a machine learning model called CLIP that understands both images and text. If you vectorize if you have two data sets exactly the same, you vectorize them using completely different machine learning models. You can't really compare between the embedding space of one to the other, because the relationships depending on if they're good models, the relationships that they encode will be similar, but depending on how they treat the data and how they process the data internally in the neural network itself, you might get completely different mappings. Um, so really, it would have to be one machine learning model that vectorizes all of your data. You can't vectorize half of your data with one ML model and the other half with another ML model, and then there's no way to search over that now. Your ML model has to be the same. Okay. So Weaviate is a free and open source vector database that you can perform this semantic search with. And the whole idea here is that your queries can be in English as opposed to in a structured query language, because the vector database understands your data with the help of these machine learning models. So an example of a pipeline that you can build with a vector database is the very first thing that comes in is your encoder. It's just another word for the machine learning model itself. And these can be from from Hugging Face. If somebody else is hosting their model, you can call it and vectorize your data using their models, or they can be from companies like Cohere or OpenAI. You're going to take your data, plug it into the machine learning model, and this is going to generate vectors that you're going to store along with the original data in your vector database. And now, once you've populated your vector database, all you need to do is, let's say somebody comes along and they have a question, you take their query, you vectorize it using the exact same model, um, and you take that query and you can locate that in the exact same vector space. And then you can do a proximity search around that query to find out what's relevant and what's not relevant, and return the list of relevant results to the user. The cool thing about this is that you can plug and play each one of these components. Right? So uh, Weaviate is pretty modular in the sense that you can choose which machine learning models you're using. You can use a text embedding model, an image embedding model, a text and image embedding model, an audio embedding model. All of these modules are available. If a module that you're looking for is not available, it's completely open source, so you can contribute and add a particular module as well. And then, of course, depending on which module, which ML model you're using, you can use any form of unstructured data as well. So in one of the demos that I'll show you, I'm going to be using natural language data from Wikipedia, and the other demo I'm going to show you, I'm going to be using image data um, from an e-commerce data set. And all of those are going to live in Weaviate in the form of vectors. The other really cool thing that you can do is, the simplest thing that you can do is just return to the user interesting or relevant results. The other thing that we've recently been working on is, instead of passing the results directly to the user, you can pass it through any other pipeline. So you can send it to something like ChatGPT, and it can interpret the results and give you an answer instead of just giving the results directly to the user. If you're interested in that, you can look at the ChatGPT retrieval plugin um, that exists. We also have a way to do that internally. We have a separate module for that where you can call a generative search module, where instead of getting the most relevant results back, we take the relevant results, we send it to ML models, generative models like ChatGPT or Cohere's model, and you get the answer back. So those are some really interesting applications where, instead of saying, tell me the top 10 things that are the most related to kitten, you can say, send the top 10 things that are the most that are most related to kitten to ChatGPT, and you can ask ChatGPT to answer a prompt using that data as context. Okay, cool. So if there's any questions, let me know. If not, I want to show a quick demo here of semantic search. Um, you can access the demo. You can scan your screen right here, and it'll take you to the GitHub repository. There's a link right there as well. Um, and I just want to show you how you can perform keyword search, first of all, uh, which is um, which is not that interesting, honestly. It's just traditional keyword search. And then I'll show you how you can do semantic search. And there's a twist to the demo as well. How is this different from other solutions like Haystack? Yeah, so the one difference is that Haystack is not a vector database. Weaviate is a vector database. So with Weaviate, you can, essentially, the two things that it specializes in is scaling up. So if you've got billions of objects, you can't do that in a framework um, that's not a database or a search engine. A vector database and a solution like Haystack kind of play together. So to scale up, you would use a vector database. There's other players in the field as well. So if you have a feature store, you can actually take your vector embeddings and store them into the feature store, bring them into the vector database when you want to search over them. That's how mainly differentiate a vector database from a solution like Haystack. It's when you want to scale up the solution, take it into production. A vector database is more reliable at scale, where you're dealing with hundreds of millions or billions of objects and their vectors. Okay, cool. So yeah, let me let me take, what I'll do here is I'll take this guy and I'll pop this in the chat so that anybody that's not on that right now, you'll be able to follow this as well. Okay. So this is the IPython notebook. So the very first thing that you're going to need to do if you want to follow along with this is um, I'm connecting to a instance of Weaviate that I've created on the cloud here. So let me show you that in a second. Refresh this. Okay. So what I did in preparation for this talk is I created this online cloud instance of Weaviate for my database, and all I'm going to need to connect to this remotely is the URL here. So notice that URL. If you go and create your own instance, it's free. You'll be able to use the sandbox for 14 days. You'll be able to pass in your your uh, your data points and it'll vectorize them for you. If you already have pre-vectorized data, you can just specify it and you should be able to use this, no problem. The other thing that I want you to notice here is that the modules that you have available. I was talking about your machine learning models and how you're going to vectorize your data. Here, you have the ability to vectorize text to vectors using Cohere's model, Hugging Face's models, OpenAI's model. So all of these come pre-built in. So if your data is not already vectorized, Weaviate will do that for you. Can this be used in line with AWS? Yeah, you can use this in line with AWS. You can actually connect, and you can see that when I go to the demo, you can take any format of data. All you need to do is batch it and send it to Weaviate to upload it, and then you can search over it. The other thing that you can also do is if you have your data and if you're developing an ETL pipeline using Spark, you can also dump your data from Spark directly into Weaviate, perform your searches in Weaviate. So there's a Spark connector for Weaviate as well. Okay, awesome. So let's one of the things that so I've got 100,000 objects already in here. I'll tell you where when I uploaded these. It takes some time to upload them, so I already uploaded them in prep for this, and it tracks how many dimensions are already stored in here. Okay. So if you open up this, this IPython notebook is exactly the same as this IPython notebook, and I'll just go through how you can go about working through this. So the first thing that you need is the Weaviate client. You're just going to import the Weaviate client. You also need access to the WCS key. So if you create your own Weaviate instance here, your API key that I'm passing in is over here. So you can click this button and you'll get your private API key. And you want to provide that through the auth API key into your auth config. So in order to connect to that instance, you need to provide the URL for that, which is just from here. This guy. Pass that in. You pass in your Weaviate API key. So this is your Weaviate instance API key. Because we're going to be using models from third-party companies like Cohere and OpenAI, you have to have accounts and API keys for Cohere and OpenAI as well. In this particular example, I'm not going to be using OpenAI, so you technically don't need this one, but you do need this one. So you need to go to Cohere's website and create a key for them. Once this is all set up, you can check if the client is ready, and you should get a true here. Okay. Next, we're going to create our database schema. And this is just similar to SQL schemas. We tell the database what to expect, what we're going to pass into it, what types of data it has. The one thing that's different here, you'll notice, so we've got properties here, as you would. So I'm going to be passing in a text format, and that's going to be the body of the article. So really what we're passing in here is, if I go forward a bit, I'll come back to this. This is my data in a pandas data frame. So what I've done here is I've taken a Wikipedia article and I've chunked it up into multiple paragraphs. So this is the same Wikipedia article, this is the same one, but this is a different sentence or paragraph from that same Wikipedia article. So you've got your Wikipedia article ID, the number of views that article has, and then the paragraph number over here. The other interesting thing here is that this is a multilingual data set. So I've got Wikipedia articles from multiple languages. In order to do this, you need to, oh, you can't download the data set from this drive. 1 second, let me make sure that everybody has approval. Okay. Mm, Okay, I'll update the link so that you can download the data set. Uh, the most important thing here is this last column. So what we've already embedded our text into vectors, and these are, I believe, 768 dimensional vectors. So each text plus the title here, essentially what we do is concatenate them together. We pass them through the machine learning model, and that gives us a 768 dimensional vector representation for the text plus title natural language. So when we create the schema, we're going to create a place that's going to, in our database, that's going to hold each one of these fields that exist in our data frame. So we need the text of the article that needs to be stored. We're going to skip vectorization here because we've already got an embedding. We've got a vector representation for all of our data already, so we can skip vectorizing this. If you don't set this to false, it will vectorize it again for you. So this is the way. If you set this to true, you could actually vectorize all the data yourself. You would have to pay for the vectorization through your API key to, in this case, the Cohere platform. Yeah. So there's a question from Franklin: Is text to vec Cohere like word to vec BERT? Yeah, it's similar. It's kind of it's Cohere's version of word to vec, except this is multilingual. So they've trained it on lots and lots of data, I believe, from Wikipedia and other sources, and it understands multiple languages. So the additional benefit of that is that you can query it in other languages as well. So that's the interesting part of this. Is TensorFlow a kind of vector database as well? No. So TensorFlow is a machine learning framework that allows you to train these ML models. So PyTorch, TensorFlow, all of these allow you to train ML models and to use GPUs to quickly train them. A vector database takes the output of these ML models, the vectors of your data, and it houses them along with the data that generated them so that you can quickly search over that. Okay. So we're going to take the text, and we essentially have a property for each one of our data points, right? We've got the title of the article, we've got the URL of the article, the Wikipedia ID for that article, and how many views each one has, and we're storing in the data type for each one of these, right? So this is a number, this is an integer, a string, and so forth. So we're going to create this schema, and we're going to pass it to our client, which exists on the cloud service. And then this is just a quick check to make sure that everything is working. Once you've uploaded your schema, it'll know how to interpret the data that you're passing in. A lot of these details are automatically set, so you don't need to pay attention to them. It just shows you that the schema now exists in Weaviate. And then we're going to load in our data. So some people are saying that they can't access this data. I'll make sure that the link is updated so that you have access to it. For now, I showed you what the database is. This is just 100,000 files from Wikipedia where you've taken the documents and you've chunked them up. we're going to set up a batch configuration. So every time you want to upload data to Weaviate, you want to batch it and then upload it. You can also do single uploads, but this is just more efficient. So we're going to take 100,000 documents. We're going to cut it up into 100,000 rows at a time, and we're going to upload 100 data points at a time. We take the data, we loop through it, and then we upload it to the vector database. And so we add the object. And so this is the part that takes some time, which is why I already imported 100,000. So once you do this, you can actually go and look at and confirm that there's 100,000 objects in this cloud instance of Weaviate. You can also run a query that tells you that it tests how many objects there are. So there's 100,000 objects in here. So now I'll show you an example of keyword search, which is what the example that I was talking about, where you search for the word Python. So here, I'll rerun this. So I'm using the like operator here, which is just a regex comparison. Here it's going to treat this string, the string avocado, and it's going to compare and look for the actual word. So here it found the word avocado in this paragraph from a Wikipedia article, so it returned this. And all you need to do is modify this. So if I give exactly the example that I gave before, if I search for the word Python, I'm just going in, taking the result, and I'm extracting the text out. And you have a match here because you have a keyword match of Python and Python. And you can pass in any regular expression here to make this a little more flexible as well. And then here, if you search for the word snake, you get a match here because you've got the word snakes in here. So this is traditional keyword searching. Now, if you want to do semantic searching, what you can do is, so I've got a function definition here that just abstracts away the actual query format here. The most important thing that you need to understand is this concepts argument, where here you're passing in uh, your topic of interest. Search the vector DB over. And then the query itself is constructed. You're querying the client and you're saying get articles and all of the properties with near text. So what this does is here it's going to look through, convert your query, whatever you pass in, into a vector embedding, and then it's going to look for the nearest vectors to that query. And so here you can query by saying, give me a programming language used for machine learning, and it's going to look through, and it gives you different programming languages here, right? Python being at the top. The reason why it repeats itself is because I've chunked up the Wikipedia articles into multiple paragraphs. So this Wikipedia article comes up twice in my query. It's just different paragraphs from that same article that come up. So you can take this and you can pass in. So here, say great movies, and it'll search over, and if it has anything that matches with this query of great movies is going to be returned. So I want you to compare this human understandable query to a SQL query and look at the difference, right? So traditionally, we would have to program the concept that we're after, and it would search through it and filter and return everything that's relevant. Here, we're literally talking to the vector database, and it understands our data. And that's really the power of a vector database. I mentioned that this was a multilingual model, so it understands multiple languages. So here, I could go in and take the query "great movies," and I could turn it into any language. So I turned it into Hindi here, and you can run this query, and so it's not. So here I think I said, yeah, great movies. Here, this is a translation for good movies. So it's returning Goodfellas because it matches with, it's a movie, and then it also has the word good in here, so it matches the most. Another thing that I can do is here. Let's see. To movies. Let me copy this guy. Let me run it and see what we get here. So if I paste this, that looks quite similar actually. Just okay. So let's see. Yeah. So you see here, it's multilingual. It's got embeddings for different languages, so you can query in whichever language. There's a lot of really cool applications for this actually. If you've got an e-commerce website, or if you've got search where you've got users that are tuning in from multiple geographies, you can cater one search function to all of them, regardless of what language they're searching over. It works for Farsi as well. So this is vacation spots in Farsi. I don't understand Farsi myself, but um, here, when you run this query, the Faroe Islands, Bahamas, you get vacation related content. So that's the power of vector databases. Right? You can take your data, you use machine learning models to embed them, and then you can search over them using natural language. Okay, awesome. So let me know if you guys have any questions. If there aren't any questions, I'm going to go back to the presentation, and we're going to talk a little bit about recommender systems. So the idea behind this is we spent the last 45 minutes talking about vector databases and how they understand your data and how you can search over your data using English or multiple languages. What does this have to do with recommender systems? And the second part of the talk is about how you can use a vector database to implement a recommender system. So let me motivate why we need recommender systems. First of all, a lot of the people here, when I asked if you understand what a recommender system is, a lot of people know about it. Um, this is why we need a recommender system, right? So if you go to the grocery store um, and you go to the cereal aisle, you've got hundreds of choices of cereal, competitors, the chocolate, all sorts of different choices that you need to make here. Right? And the fact that we have so many choices is great because the customers, users want choice. It's a competitive advantage. The problem with choice is that this is a bit dramatic. This is Margaret Atwood. Um, Choice is a double-edged sword. So if you provide a lot of choice, then that leads to indecision, which might lead to people not buying or making the incorrect choice, not going for the most optimal thing for them. Um, so the idea here is that you want to offer a lot of choice, but you also want to offer assistance when customers are choosing from the variety that you provided them. And that's exactly what a recommender system does, right? It's a machine learning algorithm that suggests the top 5 things, the top 10 things from 100 different categories or 100 different variety of items that are most relevant to a user. So it makes the problem solving of what I should buy from the 100 different options available a lot easier. If you still don't believe me, let me throw a couple of numbers at you. So there's $300 billion lost. This is from Dimitri Khan, who's a thought leader in the field, from bad online search experiences. If let's say I go to Amazon and I search for a table fan, and I don't get relevant results, I don't get what I'm looking for, I'm not going to end up buying something. So this concept of bad online search experiences, if I'm not getting recommendations that are relevant for me based on who I am, my past interactions on the platform, I'm not going to end up purchasing something. And there's actually proof to this. McKinsey ran a report, and they showed that almost one third, more than one third of all of Amazon's revenue comes from product recommendation. So when you log into their website, you open their app and you search for something, one third of the time, the things that people end up buying are just from the recommendations. Um, and I honestly can't imagine anything that would be worse for Amazon than a bad recommender system, other than their logistics network of delivery and their planes falling out of the sky. Right? Um, a recommender system is very useful, and it kind of goes underneath the radar a little bit, but you can definitely recognize when a recommender system is not doing its job. Right? If you log into a an e-commerce platform and it starts recommending things that are not relevant to you, then you know exactly that that's a bad algorithm or program underneath the hood. And if it's good, then it'll get the job done, and it doesn't get the recognition that it deserves. There's a question: is there a large distinction between recommender systems versus personalization? I'm gonna touch a little bit on this because a vector database can actually help with personalization, but from my understanding, for the most part, a good recommender system actually personalizes search results catered to you. Right? We're gonna talk a little bit about this later, but the difference between a recommendation and a search result is that a search result is agnostic of who's asking. If I search for something, what you get and what I get should be similar. If I'm asking for a recommendation, I expect your results to be personalized to my case, and that's going to be different from somebody else who's asking for a recommendation. So in my in my opinion, I think a recommender system that's good would actually take into account personalization to your use case. Okay, so let me talk a little bit about how recommender systems are implemented classically. Right? So there's many different ways, but the two most traditional ways of implementing recommender systems, the first one is a content-based filtering approach, and it's called a content-based filtering approach because your recommendations are based on the content itself, right? So let's say you have a user of Netflix or an online streaming platform, and they've watched two movies, and you know what types of movies they are. You know that they're comedy movies, they're rom-coms. You know the cast in those movies. What you can do is perform a search over which other movies are rom-coms and have the same cast, and then because it's similar in content to the movies that the user has watched, you're going to recommend this third movie to that same user. Right? And these are called content-based filtering approaches because you're filtering across hundreds or thousands of movies that you've got in your catalog, and you're filtering out the one that is most similar in content to the one that the user has already consumed, and then you're recommending this to them. This is quite different from the second approach, which is called collaborative filtering. And the idea here is that instead of just making connections on the types of movies, you're making connections across the types of users. So the idea here is that if these two users uh, historically have watched similar movies, so let's say they watch the same movies, they are now going to, if you measure how similar the users are, they're going to be quite similar because they often consume the same types of movies. So you use a user's history of interactions on your platform to build up a similarity a metric, and you pop that into a matrix, and you say, okay, which users are similar to each other, and based on their previous consumption, these users are going to be similar. And then now, every time one user watches a movie and they happen to be similar, the users happen to be similar, we now get a prompt to recommend this movie that the other person hasn't watched. And it's called collaborative filtering because now, instead of just uh, recommending a movie that's similar to movies that they've watched, you are now basing the recommendation off of similarity of users and not of content itself directly. And there's different nuances to this. You can do item to item collaborative filtering, user to user collaborative filtering, but those are details that we don't really have time to get into. Um, there's a lot of nuances behind recommender systems as well, right? And I want to touch on some of them because they're going to be relevant to our vector databases example later on. So I'm going to go through a couple of nuances behind recommender systems. The one thing that's fairly important to keep in mind is that the scale at which we're doing recommendations is mind-boggling, honestly. Um, think about Netflix. They have approximately 230 million subscribers, and they have about 13,000 unique cataloged items. In order to make recommendations to 230 million subscribers across 13,000 unique items, if you take the combination of how many that matrix, the scale is hundreds of billions, if not trillions, right? And you can argue that there's ways to scale that down where you can limit to recommender systems within geographies, within particular use cases. But even then, running this, you have to have a solution that scales up, which is one of the reasons why a vector database can actually help out. You can search over millions and millions of documents. So one of the other things that I want to show here is that in this demo that I showed here, I kind of stopped at 100,000 objects. Right? And you could argue that you can just open up sklearn in a Jupyter notebook and you can search over 100,000 objects. What's the point? So let's crank those numbers up. Okay? So this is a publicly available instance of Weaviate, and the read API key is available to everybody. You can link to this and you can query this. The cool thing about this instance is that it has 100 times more data in there. So this instance that I just showed here has 100,000 documents. This instance has 10 million documents. So if you run this same query of getting the count of objects in there, you've got about 9.4 million documents in there. The data set is quite similar. It's just Wikipedia chunked up. And you can perform a semantic search over this document exactly the same way that we did. And the query takes approximately the same amount of time. You can have a result in milliseconds, including the process of sending the query over and then getting the results back. And so the whole name of the game with vector databases is scalability up to hundreds of millions of objects. And we've tested, if anybody's interested, we've tested Weaviate at a billion object scale, and the performance holds up there. We're working on even larger benchmarking with more data objects currently as we speak as well. Okay, so now going back to this mind-boggling scale of recommender systems, vector databases can handle that scale. Okay, the other thing that we need to consider is how are we informing our understanding of the user? Are we basing it off of explicit data, i.e., surveys that we send out or comments that the user has left, or are we basing it off of implicit data? Um, whether or not a person ends up clicking on an item, whether they move something to their basket, how long they spent watching an ad for that item on YouTube. Oftentimes, implicit data is a lot more reliable because explicit data you can mess with. You can incorrectly answer a survey or quickly answer a survey and not fully complete it. But with implicit data, if I pay attention to a video, then I'm interested in it, right? If my average watch time for a YouTube ad is 2 or 3 seconds, but the watch time for a new pen or something like that is 25 seconds, then I'm interested in that, and you can more honestly get an account of my interests from implicit data than explicit data. Um, the other thing is that you almost never have a recommender system that is just a one and done type of one architecture. It's almost always the case that you have an ensemble or a hybrid solution where you combine content-based filtering with collaborative filtering. And this is one of the places where I think recommender systems implemented with vector databases can be actually very useful. Because as I'll mention, there's some places where they excel and there's some places where they fall short. And so you can combine a recommender system with a vector database in addition to your other recommender systems to augment and improve performance. One thing you have to keep in mind is diversity of recommendations as well. Okay? You don't always want to recommend the same thing. You might want to have different categories of products that are similar, but you want to have diversity, right? So if you're building up a recommender system for Netflix, and the person watches Harry Potter 1, you don't just want to go ahead and recommend Harry Potter 2, 3, 4, 5, 6. You want to have diversity in your recommendations as well. Um, we also have to consider novelty. So this is the concept of if they haven't tried it, you don't know if they're going to like it or not. Just because you don't have data on it doesn't mean that the user is not going to like it. So you might want to, let's say you're recommending 10 things, one or two of those things might be pleasant surprises, things that the user has never seen or consumed on your platform, but you suggest to them, and if they end up liking it, now you can build future recommendations for that category. More things, more nuances for recommender systems. One thing that links back to the scalability is responsiveness. For a recommender system, you have to keep in mind um, how quickly do you want to cycle in new interactions. Okay? If I watched a movie a month ago and you're still recommending things to me from that interaction that took place a month ago, your response rate is not very high. This is another thing that a vector database can help with because the CRUD support in a vector database is real time. When I insert an object, it's real time. Every time a user interacts with an object on your platform, it can be inserted into a vector database and you can get a recommender system that's updated in real time. Persistent. So if you're constantly recommending the same thing over and over again, and a user is not clicking on it, how often do you say, okay, I'm going to take this off of my recommended list and update so that now I'm recommending something else? Another thing that we'll talk a little bit about later that I want to define here is the cold start problem. Let's say somebody creates a fresh account on your platform and you have no idea who the person is. How do you go about recommending things to them? One approach is just to recommend things that everybody finds useful in general, or generally useful things, or popular things, and then based on what they're clicking on, you can go about personalizing. Going back to this concept of personalization, personalizing recommendations to that person. I believe vector databases can actually help with this as well. We'll touch on that. Um, the the largest part here, we've been talking a lot about algorithms and recommender system specific uh, details. One of the biggest things is non-algorithmic recommendation bias, right? If you're working for a company and they want you to recommend products that are uh, higher profit margin, then that's not something that is intrinsic to the wants or the consumption of a user. That's just a non-algorithmic kind of driving function that you're going to build into your recommender system. Right? So there's that also has to be accounted for. Okay, so that's kind of a whirlwind of different concepts that I want you to just keep in the back of your minds as we're going about implementing a recommender system with a vector database. Okay, so the next thing I want to get to is we spent the last 50 minutes talking about search over vectors, over a vector database, and now I'm kind of shifting over to this concept of recommendations. How is search different from recommendations is what I want us to understand. Um, and in some regards, it's quite similar. But what I would argue is that search is a objective task. It doesn't um, it doesn't matter who's asking. It's query driven. Depending on what you ask the vector database for, it's going to look up the objects and it's going to mathematically extract out the most closest objects and return them to you. So generally, search is query driven. The entire context that you need to perform the search is within the query itself. There's nothing external that you need to consider. So searching is a simpler task compared to recommendation. Recommendation is a subjective task. You have to take into account the user's preferences and product features, as we talked about in the content-based and collaborative-based recommender systems um, earlier. So the first thing that you need to ask when you're recommending a item to a user is who's asking, who is the user. Depending on the likes and dislikes of the user, I'm going to recommend different things. Whereas in search, you don't have to ask that. You just need to say, what is the query? And then I'll return things that are relevant to the query. So search is quite objective. A recommendation is subjective. You need information about who's asking. You need information about what they're asking about in order to get a good quality recommendation. So let me give you an example of this. Let's say you have a query and you search up basketball jersey. You can show any of these basketball jerseys, and this would be a good legitimate answer to this search query. Now, if you take this query and you frame this as a recommendation problem, it completely changes. So let's say the query is now exactly the same, basketball jersey. You can't just go about answering this. The immediate next question you need to ask is who's asking? Who's asking for the basketball jersey? if it's this guy who's asking, a Lakers fan, and you have a database of objects that you can recommend from, let's say you have all of these jerseys you can recommend from, one of these is the right choice, the other two are not the right choice. Right? So obviously here, this is the right choice. Right? Whereas in search, any of these could be seen as the right choice. It's subjective. Whereas here, it's subjective. If this guy was asking instead, then the Lakers jersey would be the wrong choice. Right? This would be the right choice in that case. So recommendation is quite subjective. You have to determine who's asking. You have to have information about who's asking. And this is where graph references can actually be very useful. You can encode symbolic knowledge about the person asking, about the items themselves. And then when you're searching over objects, those graph references inform what's relevant and what's not relevant to the recommendation. Okay. So in our vector database, we looked at the schema. Currently, we don't really have a way to encode external knowledge, this symbolic knowledge of who's asking. Right? The way we do that is by including graph references, right? So what we need to do is, if we've got a class for a user and we've got a class for a product and a class for a brand, we need to be able to encode relationships across classes. Right? So if a user likes a product, we need to be able to connect or have some sort of graph reference that that tells me that this user has liked this particular product, and this product has a particular brand. And so in this particular example, the product can be vectorized using a text description of the product or an image description of the product. In the demo that I'll show you, I actually take the images of products and I vectorize those images using a multimodal model. And so the number that you see here is coming from the machine learning model itself. But the number for the user is a little bit more complicated in this case. We can't just take a user and vectorize them using some description of the user or an image of the user. This vectorized representation of the user has to take into account which products they like. This concept of who's asking. And so in order to do this, we use what's known as cross-referencing in our vector database, where when you create the classes in your schema, you can give it an additional property here that says liked product, and this is going to have a data type of this class of type product, and you can add in products that the user interacts with to keep track of uh, the preferences for a user. So when you create an account and you log in and you interact with different products, your user class is going to encode knowledge about the products that you've liked, and those are going to be different from the products that I've liked. So this graph references concept is going to encode user-specific knowledge. And so anytime you have a new user and they interact with your product, you dynamically create a graph reference between that user and the products that they're interacting with. This can be a simple like of the product, or this can be actually a user who's bought a shirt and and a couple of shoes. Um, there's a question: does learning that change the user's vector? Exactly, Mark. And this is the part that I'm getting to. Right now, the vector that you're seeing here is a dynamic vector that is a function of the products that the user has liked or bought. So it's not just you pass in some information to the user to a machine learning model and the vector is generated by the ML model. No, this time the vector for the user has to be generated as a function of the products that they are interacting with in real time. So if you create these graph references, now you have an idea of how a user is different from other users and what products they like. And the interesting thing here is that because it's real time, if a person logs in and they interact with a product, you can update their likes by creating this dynamic reference. And if they like another product, you can update it and create another reference. And so now you can get an idea of who the user is. So this concept, you've basically answered this question of who's asking. The only thing that remains is, because we're talking about a vector database, we need a way to encode this knowledge in the form of a vector, because in a vector database, you have the name for a user or you have an ID for a user, and then you have to have a vector representation for that user as well. And that's what we need to get to next. And so this concept of a ref to vec is we're going to take these graph references that we just talked about and we're going to turn them into vectors, which gets to Mark's question here. We're going to generate vectors for that user using the products that they've liked. So each one of these products has a vector that can be generated from a description of the product or an image for the product. We need to use the products that the user has liked to generate a vector for the user. And so anytime somebody interacts, it's going to update their vector as a result of what they've interacted with. And this goes back to the responsive concept that I talked about. With a vector database, the minute somebody clicks on a new product, you can update your your understanding of that user, and as a result, update your recommendations to that user. So I'm going to go through the math behind how ref2vec works exactly. And, and the idea here is that the user, the identity of the user is not based off of their um, information that they've provided, their description, but rather what items they've interacted with on your platform. So if that's a little confusing, let me give you an example. So let's say you have a user who's come into your platform, they've logged in, and they've clicked on or they've bought two items. They've bought a shirt and they've bought a pair of shoes. Both of those items have vectors. In our example that I'll show later on, those these vectors are generated from images of the products themselves. So both of these objects have vectors. Let's take each one of these vectors and put them on the side here. We can use these vectors to generate the vector representation for the user here. So how we do that is using a centroid methodology here, which is the simplest form. If I've interacted with two items, my vector, the user vector for this this object here, is going to be the average of all of the vectors of products that I've interacted with. So here I just add up across the dimensions of vectors, and I've only showed 4 dimensions here, but this is 300, 700, 1000 dimensional. So you can take a per dimension averaging of all the features and you get the centroid vector across all the products. And now this vector is how you represent that particular user. So now we have a vector for that user based on their immediate interactions. And so now when you go to making a recommendation, all you need to do is employ a user as a query methodology. The user and their vector representation, which is the average of all the products that they've interacted with, can be queried. And you can simply say to the vector database, give me the objects that are the closest to this vector. And this vector is the user itself. And so let's say you have a pair of shorts that are the closest that the user hasn't already bought. This is going to be our product that we recommend. And if you say, give me 5 closest items, you'll recommend 5 of the closest items. And the interesting thing here is that once you've recommended this item, let's say the person ends up liking it. Let's say they buy it or they put it into their cart. You can then take that interaction and you can update your representation of the user using this new product's vector representation as well. So now the identity of the user gets updated in real time. Yeah, exactly. You this takes the you are the product to another level. Right? The identity of the user is the products that they interface with and updated in real time. Okay, cool. So if there's no questions, I want to show you a demo of this recommender system implemented. Um, okay, so there are some questions. How does, say, Netflix or Amazon do this? Do they have machines with GPUs running 24/7 to update the user embeddings? So currently, I don't know if Netflix or Amazon uses vector databases to do this. I do know that they implement content-based and collaborative-based filtering um, with deep learning implementations, but I don't actually know if they use vector databases, honestly. Um, the user vector must include the item that they are searching for. So let me go back here. No, so the item that they're searching for need not be in the user's definition. So the only thing that you need to know is what is the vector representation for that user. And then you can say, what other items in my vector database? So let's say you're running an e-commerce platform. You have all of your products vectorized and stored in a vector database. You're just going to look up and see what is the closest uh, product vector that the user hasn't already bought. And let's say that the shorts here are not in the representation of the user. They're just the closest next product that happens to be close to this vector. But once they do, let's say they end up liking this recommendation, then you can update the user's vector using another product that they've liked. So this is after the fact. Uh, what's the difference between this approach against two tower models for recommender systems? I'm not sure. I'm not sure about the two tower. Can you tell me a little bit more about the two tower model? Or maybe we can connect offline, and I can understand that a little bit better. A next question from Nick is, but I could return hats. Oh, 1 second, hats instead of shorts. Yeah, so this is it completely depends on who the user is. So let's say instead of interacting with a shirt and a pair of shoes, they interacted with two hats. The third, let's say you have a third hat in your vector database, that hat is going to be closer to the user vector in that case, and you end up recommending that hat. So depending on the user and the items that they've interacted with, your recommendation gets updated as a result of that in real time. How do you solve the cold start problem if you have a brand new user? So yeah, so that's a good point here. In order to form, so let me go back here. In order to form the vector for the user, they need to have interacted with items on your platform. the the cool thing here is that because it's happening in real time, let's say a user lands on your front page and you show them a list of popular items or a list of categories. The minute they start interacting product by product, you can start personalizing your future recommendations in real time within milliseconds, because all you're doing is performing one query. You're querying the underlying vector database. The other thing you can do with this is you can perform a session-based recommender system where, regardless of whether or not the person has a account on your platform, let's say it's just the person who's using incognito mode to surf and access your platform, you have no information about them. The minute they go to your platform and they start clicking on a couple of items, you can re-rank all of your product catalog based on the interaction that the person has had within a minute on your platform and start recommending. So the answer is, if you have no information about the user, then you can't do anything. But this is a lot more responsive than traditional recommender systems, because you can take one interaction and that's enough to solve the problem. They can literally hover over one item and you can re-rank your recommendations based on that interaction. Any other questions on this? If not, you can scan this, and this will take you to another GitHub repository, which is the e-commerce demo. So I'll go through the code for this first of all, and then I'll show you this in implementation, and I'll talk about some of the advantages and disadvantages to this approach. So over here, if you scan that, what I'll do here is similar to what I did before. Let me copy this guy, and let me paste this here. There it is. Okay. So if you click that link, that should land you over here. You can clone this or fork it. And we're going to do a couple of things here. You're going to take all of the images for our products that are going to be featured on our e-commerce platform. You're going to download them, put them into the corresponding folders. There's a bunch of requirements here. There's machine learning libraries, as well as the actual client and server side uh, packages that you need to install. You can install them all just by looking through the requirements.txt or running this one command. That should be enough to get you everything to get started. So if you look at the images actually, so here, If I go in, images. So this is what our images look like. These are all the products that we have in our database. And we're going to vectorize these images. So the vector database is going to store the images as well as the vector representations for these images. So just product does not work with straight pip, requires conda. I think some packages, okay, I'll update that. I think some packages might not be available with pip. I'll also include a version of virtual environment to make it easier for everybody. Okay. All right, so this is our data. And then what we're going to do here is, so let me go back here. What we're going to do here, let me close some of these. We're going to create a schema. So this is the first thing that we do. And in this case, we're going to run Weaviate locally. So it's not going to be on Weaviate Cloud Services. We're going to run it locally. And we're going to use a Docker file to do that. Dockerfile has a lot of the modules that we've got enabled here. So we've got the ref2vec centroid module that we talked about that is going to take our referenced objects and create vectors for our user classes. We've also got multi-to-vec clip model. This is the machine learning model that takes in images and text and it turns them into vectors. So we're going to create our schema here. The schema is pretty straightforward. Let me walk through it one by one. So we've got mainly products in our schema, where you have a product, and then we're going to vectorize this product using a multi-to-vec clip model. And we have the image for the item itself that I showed you earlier. We've got information about the product, so we've got a description for the product. We've got a location of where that product is stored on our repository. We're skipping mostly everything here because we're only vectorizing the product using its image. So we're going to vectorize our product using the multi-to-vec clip. So that's straightforward. The second thing we have here is another class. So this is our entire product class, and it's vectorized using a machine learning model. The more interesting thing here is the user class. So when somebody logs onto the app, they're going to create a user class. It'll automatically be created for them. And they have a session number here, which is automatically allocated to the user. But the one thing that they also have, the other thing they have is this cross-reference, an item that they've liked. When you land to the app, you're not going to have an item that you've liked, but it's responsive. So every time you click on an item, it's going to add it to this liked item, and it's going to create a reference between the user and the product. So the way that the way the database knows that this is a cross-reference is because it has a data type of product, which is the first class over here, right here. And this is what sets up the cross-referencing in our schema. So we're going to create that schema, and then we're going to upload our data. So if I go to the upload data file, the one thing that you need to be careful about here is that the images cannot be uploaded or vectorized directly. They have to be converted into base 64, and then once they're converted, then they can be uploaded to the vector database. So I've got a function here that goes from takes images from what I've shown you, and it turns them into base 64 before they can be uploaded into the vector database. Everything else is pretty similar to what we looked at for the other vector database, where we're going to take all of the metadata for our image, so the category, the name, price, quantity, so on and so forth. And we're also going to take the image and we're going to pass all of these in, batch them, and pass this into our vector database. So the items that we're passing in here follow the schema. So all of these get inserted into the database. I think once you run this code, it takes about 3 or 4 minutes, depending on your system, because the vector database is locally running. It might take longer or shorter. Okay. And then once you've got this, then you can go in and run the app, which is a pretty simple app locally, and it's going to start up on localhost port 8000. And once you start that up, this is what it will look like over here. And so you've just got a random sampling of some of the products, and you've got a distance to the centroid metric that will get uploaded. The first thing that we're going to check here is image search. So I can pass in a query here, and I can say watches, and I can search for it, and it's going to take the word for watches, represent it as a vector, and then it's going to return images. And that's the cool part of the multimodal model that I'm using here. I'm actually searching for a word, but it's passing me back image representations. It doesn't actually know that these are watches, but it understands that the word watch is similar to this image of a watch. Uh, Now, the other thing that you can do here is once you've kind of searched for this, so let's say we do activewear, we get activewear here, and then I can start clicking. And every time I click here, if you go to the app here, you're calling this image clicked endpoint, and all this does is it updates the references in the underlying vector database in real time. So every time I click something, it's going to check if it's already been clicked. If it's not already been clicked, it's going to add a reference to the liked item for that particular user. So it's going to use the user ID. It's going to add a liked item for a product ID. So if I go here, I click one item. It has now this item has a centroid distance of 0 because there is only one item, and the average my vector representation is the average of all the items that I've liked. I've only liked one item, so the distance from that centroid is 0. And it's re-ranking all of my other products as a result of what I've included here. So now if I click another item here, let's say I click the shorts, it's going to, in real time, re-rank everything based on the two items that I've clicked. And now the centroid is in the centroid of my user vector is in between. It's the average of the two items that I've included here. And you can keep on clicking. You can deselect items as well, and re-rank them. So let me go here and let me just end off with a couple of takeaways here. So the users are vectorized. Your identity of who a user is in your vector database is based on references to the products that they've bought or they've liked. And then it's very low overhead in terms of recommending things now because you're taking the vectorized representation of that user and you're querying the vector database with that one vector. And this is the simplest form of vector database querying that you can perform. It's just a near object search in your vector database. And you tell the vector database to return the K products that are in close proximity to that user vector. And the interesting thing here is that, like I demonstrated, you can keep this up to date in real time. So as user preferences are changing, your recommendations can change in real time. So I want to end off with a couple of advantages and disadvantages here, which I think will be instructive to how you can implement this and how it can work with your other recommender systems that you already have working in production. Some advantages, I think scale is probably the most important advantage here. The ability to do real-time recommendations over hundreds of millions of objects um, is a significant benefit here. If you've got hundreds of thousands of different objects in your e-commerce platform, and to be able to update recommendations in real time, this is a big benefit. It's very low overhead because the querying that you're doing is the simplest form where you're doing near object querying. You can update in real time as the person is interacting with items on your platform. It kind of addresses the cold start problem because the minute a person interacts with an item on your store, you can start recommending relevant things, similar things to them. You can also use this to augment your pre-existing recommender system, right? Because this is a very good solution to short-term personalized session-based recommendations. It's not a very good approach to long-term solutions, as I'll talk about. So what you want to do is augment your longer-term recommendation solutions with this short-term recommender engine. You can also have multiple instances of the same user or multiple users. Exactly. So Mark just brought up a very interesting point. That's actually on my list of shortcomings. It's number one on my list of shortcomings, actually. The problem with this approach, at least with the centroid approach, is that let's say you have a user that has very varying choices. Let's say you go on and you buy a PlayStation 5, you buy a pair of shorts, and then you end up buying I don't know, a watering hose or something like that for your plants. Now the centroid is going to be in no man's land somewhere in between these three types of products. So that centroid is not going to be a good representation of the user's preferences. Right? That's one of the shortcomings of this. You can think of a different approach where instead of doing a centroid vector, you can do a clustering over the product to recommend from those different clusters instead of literally taking the average. That could be a potential solution, but this is one of the shortcomings of the example that I presented here. Another problem with this is that it lacks diversity because your user vector is the average of the vectors of products that they've interacted with. It necessarily means that you're recommending things that are similar. You're not going to be recommending a wide diversity of products. The other problem here is that um, it's the quality of recommendations you get is going to be largely dependent on how you vectorize the products. Here we vectorize the images themselves, but if you had taken a very large description of a product and you vectorized that using that, you might not get as good of a result. The more specific the vectorization is, the better the recommendations that this process yields. The larger the chunk of text or data that you're vectorizing, the more difficult it is to capture user preference using this centroid and averaging of vectors methodology. Young says, concat the vectors. The top K recommended items are separate from each other. How do you address the diversity and novelty of features you mentioned? Yeah. So the problem with the centroid approach is that it doesn't have a lot of diversity. If I buy two shorts, it's going to recommend to me all the other shorts in the platform. So you have to concatenate or you have to aggregate the product vectors in a different way. You have to have some sort of function over diversity. So you could look at vectors because if you look at the demo here, you also know which items are farther away to your centroid here. So you might be able to implement a function where now you have for objects that are farther away, you might be able to add those into your top 10 recommendations as well. And you can also do that for diversity because in the metadata of the app, you also have the category for the item as well. So you can say top K recommendations, but only recommend two from a particular category. If you want to include novelty, include one item that is farther away, or at least a threshold distance farther away from the items. Um, the cool thing is that you can come up with these types of solutions because you can quantify how far or how close any one item is in your entire vector database. So you can have separate calculations that encode for novelty, for diversity, and then you can add that to the simple approach that I'm showing here. Exactly. All right, folks. We're a bit over here, so if you want to carry the conversation on, connect with me on Twitter, LinkedIn. Um, Feel free to tweet questions at me. We can connect. I'm available on the Weaviate platform as well. You can send me questions later on. I'd be happy to connect and answer questions you have. Um, thank you for everybody. Thank you for the interactions. I love the questions that were coming in. It's made this really fun. And give us a follow if you like the project. It's completely open source. You can start using it. You can start contributing to it. And if you do end up building something cool with it, we'd love to hear about it. Thanks, everybody. And you can also you're going to get a link to the feedback for this session. So if you enjoyed the content, if you like the session, feel free to share feedback. Thanks, everybody. Thank you for your time. Yeah, you guys can scan the QR code here and provide feedback. Thank you, folks. Look forward to connecting with everybody. Have a great day.